Hi everyone, we're about to do some problems that involve mechanical equilibrium, and before we do that, let's describe mechanical equilibrium. It's a state when you have a rigid body, so we're not talking about anything squishy or floppy. We're talking about something that the internal structure is strong enough that it will actually hold its shape. And we're talking about something where all the forces on it are going to be equal. And so you end up with all the forces in the x direction or horizontal direction equals 0. All the forces up and down equals 0. And all the torques on the object equal 0. So if you look at this really cool little sculpture made out of rocks, all of the forces down, all the individual forces of gravity, equal all of the normal forces that are being produced upward. Any force to the left is going to be equal to any force to the right. But we can also include one more statement that we're going to explore mathematically, and that is torques. Anything that is going to make the whole system rotate one direction will be equal to anything that makes the whole system rotate in the other direction. Well, what causes rotation? That's going to be torques. This is just a little diagram of a loading on a big aircraft, and everything, the weight and balance, all has to be over or above that point of support, which happens to be a wing on an aircraft. So when you're building or constructing anything as simple as something cool you did at the beach, a big building, or doing weight and balance on an airplane, you have to worry about mechanical equilibrium. Now when we do these calculations, how do you start? You start by drawing all the force vectors. So if there are force vectors involved, you draw them. If the object itself that is holding the other things, the teeter-totter itself, it has weight, it has a force of gravity. If there's any a force that is applied at some sort of an angle, we need to resolve that into vectors because we want the component of the force that is perpendicular to our lever arm. When we measure our lever arms, we measure lever arms from our point of support. So lever arm is going to be this distance for this force, that distance for that force, and this distance for that force. If they are objects that have some size and shape, we go to the center of mass. When we're doing mechanical equilibrium problems, we also have to choose an axis of rotation. Now that's going to be the mathematical point that we're going to sum our torques around. It can be any point along the lever arm. It can be literally any point we want. It can be either end. It can be the exact center. It can be the fulcrum. It can be at one of the weights. It's a mathematical point, and the situation hopefully will help dictate what is most convenient and logical to use. We also, if we're trying to calculate the best position maybe to add this green weight for stability, we're going to have to determine what is going to be our pivot. Now, a fulcrum is kind of that natural pivot point. If you've got a teeter-totter setup, well, yeah, there's definitely a natural pivot. But some situations, and we will do a couple problems like this, they're not designed to rotate. They're not ever designed to rotate. And so we don't have a natural pivot point, and so we're going to do our math around a mathematical axis of rotation, not a obvious pivot. And any force that happens to be perpendicular to the axis of rotation does not cause a torque. What I mean is this: for this bar, the actual bar that is acting as my lever arm, that's holding up my other weights, it will have a force of gravity vector. And that bar itself, if it is acting directly over the pivot, it will cause no torque. And the reason it's not going to cause a torque is because of the fact that torque is force times lever arm. Well, if the lever arm is 0 because it's on the actual point we're choosing to call as our mathematical pivot, it's not going to cause a torque, and it will fall out of the equations. That can be handy if we're dealing with a complicated problem and we want a variable to disappear. So those are some general guidelines. Next, we're going to go forth and we're going to do some math problems.